So I'm actually a climate scientist, not a lobbyist, a climate scientist, and I live in Tasmania, and Tasmania actually is a home of a very big community of climate researchers, particularly in oceanography and around Antarctica. And I've been very lucky actually to have participated in the Inter-Governmental Panel on Climate Change. In 2007, you might remember Al Gore actually won a Nobel Peace Prize, not anything else. And IPCC, not me, IPCC also won that Peace Prize. It was shared with Al Gore. So IPCC is all about actually bringing all the evidence that we have in the literature, in the research literature, and writing it up as a kind of a summary. And I'll describe a bit of that process in a few minutes. But that summary is what is communicated through what we call a focal group, a little bit like perhaps one for every electorate, but this is one for every country, carried out by the United Nations with the World Meteorological Organization. So this partnership between the United Nations and World Meteorological Organization has created this Intergovernmental Panel on Climate Change. And every 5 years, it basically delivers a suite of reports, which are basically a statement about how the Earth has changed in the last 5 years. And it's been going since 1992 through to the present, and they're very influential. So in particular, I participated in this report, which is the special report on oceans cryosphere in a changing climate, and that was released in September last year. And this report was the first one that kind of covered off on the oceans, the polar regions, say the Antarctica and Greenland, the frozen permafrost, the high mountains, and the oceans themselves, from the surface to the deep, and from the polar regions through to the equatorial region. And this is that report that came out in September. And the front cover is the picture you saw in the opening slide, and the back cover, if you look at it, is really representing these key critical ecosystems. This is a report. It's not just about the physical world, but it's also about its interactions with these ecosystems represented by the fish and the reef here, but also interactions with human communities. So this is a report that isn't narrowly focused on the science itself. It's actually about how the science goes to the ecosystems, goes to the human communities as well. And this is a sort of a summary of that report, but the key, I won't talk about the high mountains, but the key thing is it covers off on the oceans, covers off on sea level rise and the impacts for low-lying islands. I led the chapter around the ocean marine ecosystems and those dependent communities. And then, you know, you've heard of things like marine heat waves, and this is an emerging idea, if you like, and we're recognizing that there are extremes and abrupt changes going on, and these will also have impacts exacerbated by climate change. So these reports, you might think, are things that is just written by a few people, but actually they're very symbolic of a collaboration, a little bit perhaps with some of the same underlying principles as CCL. We had in this report, and this is one of the smaller reports, we had 104 authors involved in the meetings. Gender and diversity are really important things, and so 31% of the authors are actually women. They come from, these people come from, the researchers who are involved, the lead authors, come from 36 different countries, so both developed and undeveloped countries, developing countries. Now, some of you might not understand, but actually research literature has absolutely blossomed. So in this report, we assessed literally 7,000 different research papers to distill it down to basically 10 pages of what we call a summary for policymakers. And that 10 pages is the critical element of the report. Now, if you think about how hard it is to convince all the nations to agree on something, the summary for policymakers is exactly that. We, over a 4-day period, were in Monaco, and every word and every line of that summary for policymakers was gavelled down by agreement across the 195 participating United Nations countries. So I want you to think about that. There's 3 or 4 of us at the front who are showing the words, and in the room, they actually agree with some discussion. And over 4 days, we had to actually agree to every word. And if you don't agree on the words, they actually fall off. So your important results, the important elements of the summary for policymakers might suddenly fall onto the floor and never make it into the publication and being released for wider distribution. So it's an incredible effort. And typically what happens is that you get through about 70% of the words on, you get through, 20% of the words by day 3. And then you work a couple of full nights to get to the final conclusion. And these reports, so it's sort of heroic stuff on the day. And then the next day we actually have a press conference and the report is actually released and distributed to the world. And this report, like all of the IPCC reports, is actually more thoroughly assessed than the typical research paper that a climate scientist might write for publication. So there's a huge effort to make sure that these assessments are very robust, very reliable statements around the science. So we already know from all the earlier reports and much of the literature that there's already extraordinary things that have actually changed. So the CCL is interested in lobbying for a mechanism to respond to climate change, but actually the evidence for climate change is quite extraordinary. And what we actually know is that if this was sort of a picture of the Earth system, right? So, you know, there's some ice sheets here, glaciers, high mountains. In the Northern Hemisphere, there's permafrost. There's the atmosphere, which is increasing in carbon dioxide from the emissions from burning fossil fuels. But we know actually about a third of it enters into the ocean. And that third that enters into the ocean is actually causing the pH of ocean to decrease. So the ocean's becoming more acidic. Because there's an excess of radiation at the surface of the Earth, it's actually heating up the ocean. And you might not quite appreciate it, but more than 90% of that heat is captured in the oceans, and it actually inhibits the changing surface temperature of the Earth itself. So the oceans play a really critical role as a service in kind of holding back the temperature, and as the oceans heat up, they store carbon dioxide that's emitted by humans. That comes at a cost of decrease in ocean acidity, increase in ocean acidity, decrease in pH. And because the surface waters are becoming lighter, it makes it harder for the surface to interact with the deep ocean. And so, in fact, we can, amazingly, I think, measure that there's a decline in the amount of oxygen going into the ocean. So our ocean state, and it's a big, thick ocean, is actually evolving. And one of the things that happens when you warm up the ocean is that the ocean actually expands. And so sea level goes up by the thermal expansion of the ocean. And because we're melting the ice sheets have actually lost mass, but because they're on rock and on land, that loss of mass drains into the ocean and adds to the sea level as well. And so you can see that, and we can attribute these changes in the atmosphere and the changes in the ice sheets to human activity. And so what we're finding is that almost everywhere we look, and this was in the earlier reports, where we look, we find that there are changes occurring, and many of those observed changes can actually be formally attributed to human activity. So this is the starting statement for the CCL, right? The starting statement was that climate is changing. Well, yes, it is changing. And in the case of these reports, we actually go to a lot of effort to understand how humans have induced much of those change. So one of the key messages that comes out of this report of that growing literature is that the world's ocean and cryosphere have been taking the heat. It's kind of a pun here from climate change for decades and decades. And we, because we can measure it, we can actually see that there are consequences for humanity, and I'll illustrate a couple of those in a minute. The polar regions, which is particularly close to me in my current job as the program leader for the Antarctic research at the University of Tasmania, is actually changed quite significantly. Greenland and Antarctica in the year 2000, we barely knew it had changed its mass, and it had actually lost mass. And now we understand through measurements from space and direct measurements on the ice sheets themselves, that they're losing mass, and that loss of mass is actually accelerating. All the new estimates have got faster. And there's an enormous volume of ice locked up in Antarctica in particular, 58 meters. If we melted the whole of Antarctica, we could actually increase sea level by 58 meters. I'm not saying we're going to do that. Actually, the estimates I'll show you in a minute are about 3 meters by 2300 from Antarctica alone. Arctic ice is declining and opening up the Arctic Ocean. And it turns out that if you think about it, we're trying to limit through the Paris Agreement the temperature of the Earth to be 2 degrees or less. That's the Paris Agreement. But if you only warm it up by 1.5 degrees, half a degree doesn't sound like much, but actually it has a big impact on the state of the Arctic Ocean, for example, and there are other impacts. So half of a degree means that the Arctic Ocean would be rarely free of sea ice in the autumn in the Northern Hemisphere, whereas if we went to 2 degrees, we'd cross a bit of a threshold, and in fact, it would be very frequently free of sea ice in September. So small changes can have quite significant impacts. And the ecosystems are also being observed to have changed. And in the case of the Arctic, where there are lots of indigenous and dependent communities, they are also impacted through the, food provision. So the polar regions are actually quite sensitive. Now, the Antarctic, which has very few people in it, but it's a huge part of, like a climate flywheel, I could almost say. So this is my view of the world. Tasmania's here, of course, right? So I'm staring at Antarctica on a daily basis almost. But the Antarctic is actually a centre of a huge current system that flows circumpolarly around Antarctica. And just north of that current system, there's this preferential uptake of heat. This heat is actually masking it's slowing down, if you like, the change that we would otherwise see. And it turns out that the Southern Ocean is taking up 35 to 43% of the total heat that's stored in that system, and despite the fact that it only occupies 25% of the area. And in the last decade, the Southern Ocean was taking up 45 to 62% of the heat. So the Southern Oceans are an important aspect of our climate system, and disproportionately so relative to other parts of the Earth. And indeed, that's a good reason for investing in research in that area. But it's also a place that we can kind of understand where human influence is. Now, one of the things that you might, this is a very complicated kind of figure. It comes out of this assessment of the literature, but it's actually quite easy to think about in a way. These are sort of regions up the top here. These are regions around the world: tropical Pacific, the tropical Indian, tropical Atlantic, Southern Ocean, which is an area of my interest, but also the Arctic. And forget about this top box, which is about physical changes, but let's look at these changes in ecosystems and the changes in human systems and ecosystem services. So what this is really saying is this is about the marine living things that we should care about. And here's how those marine living things with the physical change interact with the sorts of things that we should care about, you know, fisheries, tourism, cultural services, around the value of these environments. And coastal carbon sequestration is really about kelps and marshes and mangroves, depending on where you are on the planet. But the interesting thing, which is sort of emblematic of the Arctic and the Southern Ocean, is that many of these are considered to have positive changes. So blue boxes are positive, and the pink boxes are actually negative changes. This is the only sector of the Earth where warming it up is considered to have even positive changes, right? And then everywhere else, it's basically negative changes. So there's this kind of message where positive and negative can be a little bit ambiguous, but there's this message that actually the high latitude polar regions have some beneficial changes that go with climate warming of the climate system, but actually everywhere else, they are basically negative changes. And I'll illustrate that in a little bit more detail in a moment. Now, sea level is clearly of a concern. There are, in the small island developing states around the world, there are 65 million people who live there. Within 1 metre of sea level, low-lying countries, Bangladesh, for instance, but also much of Europe, there's another 680 million. So about 12, 13, 14% of the world's population live somewhere very close and can be affected by sea level rise. Now, I talked about how Antarctica and Greenland, which is so far away, are melting, and they contribute their mass, and the oceans rise up. And over the last century, the rise has been about 17 centimetres, so not very much. Forget about this figure here. We'll just look at this figure here. What you can see is this is the projections. Now, these projections are based on our understanding of the science through numerical models. They're carefully calibrated against what we understand from the last century. So there's a lot of knowledge embodied in these two projections, and they're policy relevant. This is if we chose a high emission scenario. And this is where if we chose a low emission scenario. So this blue line here is actually the one that would meet the Paris Agreement of 2 degrees of global warming. So you guys, I'm hoping, will lobby sufficiently well to move from this high emission scenario to this low emission scenario. And I'm keen that you have that kind of success, because there's a huge difference between this high emission scenario and the low emission scenario. In 2100, 0.84 metres is the average change for sea level globally, right? Doesn't sound much, but I'll show you how significant that is in a second. and it's much lower, it's 0.43 metres by 2100. But if we continue to warm the world in an unabated way, along this policy trajectory, if you like, we could have as much as 5.5 metres of sea level rise at the worst, or as low as almost 2.5 metres of sea level. And if we had the low emissions trajectory, it'd be 1.2 metres and maybe less than 0.9 metres. So these are two different choices the world could choose, depending on the success of CCL to lobby. But it's really a choice, if you understand. These are scenarios of possible futures that come from the changing and melting of Antarctica and the heat that goes into the oceans that causes sea level to go up. Now, last century, we had 17 centimetres sea level rise. Now, I want you to think about what a 1 in 100 year storm surge would be. So in the historical past, we'd often have storm surges and they'd occur 1 in 100 years, okay? Now this figure, forget about this figure. This is just the high emission scenario, and this is just the low emission scenario. And what this figure shows is the year, what used to be a 1 in 100 year storm surge became every year, right? So this is, something that was almost infrequent is suddenly occurring every year. And what this picture shows is every year would be in the year 2000. So what you can see is that many places around the world, it's already changed the historical 1 in 100 year storm surge to every year. Wherever it's black here, it's actually already happened. So that 17 centimetres has already changed the landscape of sea level rise for many of storm surges for many, many small islands and coastal regions around the world. And if you continue on into, say, 2050, it's this sort of orangey colour, you can see a huge fraction of the world has actually changed from the old historical 1 in 100 years to every year. So this is already showing us that for the low-lying areas, climate change is actually changing the storm surge frequency enormously. And so one of the key conclusions, I'm going to talk for too long, so one of the key, so I'm going to skip some parts of this, but one of the key conclusions is that for many low-lying coastal islands and small islands, they will be exposed to risks of flooding and land loss annually over the, rather than 1 in 100 years by 2050. And that really requires a strong adaptation response. And you can actually think about what are the sorts of responses you might do. And there's a lot more in that particular report about this. You can, of course, use engineering, build retaining walls. You can accommodate by lifting up the sort of infrastructure you might build. You might harden up dunes with ecosystem-based adaptation. So you might plant mangroves, you might plant grasses into dune systems, you might protect through those sorts of methods. You might actually build the dike out into the ocean and so advance. Or in some case, you might have managed relocation. And I tell you, in this summary for policymakers, some very small low-lying islands got up and were very upset at the prospect of relocating because they had nowhere to go. And you can see there's some really tough decisions in some of these sorts of thinking for the people who live on these various small island developing states, for instance. And one of the things that we found typically was that the people with the highest exposure and vulnerability, which typically is in the equatorial band or the close to the equator, were often very vulnerable, most exposed, but had the lowest capacity to respond. So there's sort of an inequity in the way some of the climate signals and the adaptive response that's possible by those affected communities. I'm possibly running over time. Andrew, tell me how I'm going.
Yeah, probably another 5 minutes, and then we'll take some questions.
Yeah, so why don't I now just skip on to talk a little bit about food, and I can talk a lot in detail, but I'll just show you these two figures here. This is around the potential catch of fish going into the future. So this is a source of nutrition for 20% of the world's population. And you know, there's a lot of sophistication behind that, but this is kind of a summary message that you get out of it. This is the change. This is the decline in the catch potential. So it's kind of a measure of the amount of sustainable wild fish that we can maintain in the ocean. And here is the average temperature change. So for a 2-degree temperature change, you can see that there'll be a 5-degree, kind of on average of 5. It's just sort of a bit of a range, 4 to 8%, roughly 5% decline in the total global catch from wild fisheries. So we have a dual problem, of course, populations going up, and the sustainable catch limit from the natural oceans is actually going down with climate change. And it's not just the catch that's going down. The other thing that's happening is these species turn over. Actually, they grow faster, die faster in a warmer world. And so this turnover rate also changes. It's not an accident that the old pictures of old fishermen have big fish in them, and now in the modern world we actually have small fish. It's partly the human activity, but it's also in part because it's warmer. And you can see in this panel on this panel on the right, that if we chose the low emission scenario on this change in biomass, you can see that it's a much lower impact. It's still negative compared to the high emission scenario. So there's already knowledge that understands how the food web will actually change on global scales. In the high emissions case, it's going to be 15 plus or minus 6%, right? So these are non-trivial changes in the available catch. Now we have fisheries management and protected areas, so they actually offer opportunities to protect our supply of fish, and there's also alternatives in the form of aquaculture, which is another story. And then I'm going way over time, but I can talk about this picture. This picture is really trying to address what happens in the coastal regions around the world. And there are many kinds of ways that the coasts are affected. They're affected through extreme events. They're affected through sea level rise. There's also, over the coastal waters, a deoxygenation of the surface waters, different to how I described earlier, but it's a deoxygenation. There's rising acidification, lower pH, and warmer. And all of these things tend to occur in a way that stresses everything additionally. They compound the problems. So it's not just a problem of warming, there's all of these things. And if you look across all of those ecosystems that I talked about, warm water corals, highly vulnerable actually to very small changes in temperature. Kelp forests are already established as being in danger in places with high confidence, but with a rising temperature, there'll be increased level of impacts. And we can go across all these different ecosystems, even to the deep sea benthos, which is actually more connected to the surface waters than we've ever understood. And all of these are increasingly at risk. The projections take us beyond 4 degrees with a high emission scenario. They take us to 2 degrees for the Paris Agreement. So you can see a lot of systems are already exposed and vulnerable to these small changes. And if we limit to 1.5, then we actually mitigate and reduce the damage against these slightly less sensitive ecosystems. So there's some huge policy insights that come out of this sort of work, but some of these would resonate with what the CCL is about. It's clear from all the research that we do that for these adaptive responses to climate change, it's absolutely essential that people, communities and governments are empowered to understand the transitions and the adaptive response they need to make. And it's incredibly important to have multiple sets of evidence. It's quite easy to actually make adaptive responses which you think are good, but they're actually maladaptations to climate change. And so it's really important to actually provide and combine this evidence. And weirdly in my view, because I'm a hardcore scientist in many ways, there's this focus actually on the importance of education and climate literacy. And I'll just finish there, Andrew, because otherwise I've talked too long. Thanks.
Thank you for watching. Please subscribe to our CCL channel by hitting the button in the top left-hand corner of this screen. Spread the word of CCL by using the share icon to as many of your contacts as possible. Thank you. See you next video.